Hey, how's everyone doing today? It is the start of office hours. Hey, Sierra. Hey, Sydney. Hey, Knox. Hey, Aisha. Hey, Stevie. Hey, Michelle. Hey, Jessica. I'm out of coffee. I got the second cup of coffee a day. We're waking up Mubot. Meath, good to see you here. I think we're going to do some project to start. Oh my gosh, the sound effects are so loud. Oi, got to take care of my ears. Good to see you here, Isabel. How's everyone doing today? Should we start with some Statuon project? That's kind of been Mubot is in the chat. Is he awake? He is awake right now. He's saying, I am Mubot. Did the points go out? The points didn't go out. I clicked the points too quickly. You got to wake up Mubot. You got to get those points. You've even got Florida in the chat. What? Kirsten, good to see you here. We got a new emoji. Florida. We got Bunny. Florida. Could you do a couple questions from chapter 17? Yeah, person moves to a big city. Jessica, let's do it. Should we start with the project? Let's do this. Project or chapter 17? I'm putting the chapter stat to 1 and we can do some 474. We're gonna have the assignments released later today. So we've got project or chapter 17. Project first is fine. Oh, cool. We'll see. Let's pull up the project. I've got too many tabs open on my computer. We had 6 responses last night. Oh my gosh. Ooh, someone says they got an armacy of 0.069, like around 1200, I believe. I think some people didn't transform their, I think they transformed and they didn't back transform. If you're in 474, we have some people saying they've got armacies of 0.0 something. And I'm like, I don't know if you got an armacy, if you got an armacy of 0.0, it's really low. Really low, 0.06 or something armacy. But hey, if they did that and they got it, wow, that's amazing. I'm interested to see these models here. But we had 6 people submit for the bonus. And we'll see. It looks like a lot of them are getting around 1,300 something, which is pretty good. So interested to see. Let's see. Your armacy, what was it, Sydney? What was it? It was like 13, 1400? 13, 1400 was about what I expected. I was hoping someone would get in the 1200, 1300. Yeah, great job, Sydney, right there. Yep, sounds like you did it right. That's I'm a little afraid if someone says they got an armacy of 0.02 because that means their typical miss on bike demand is like a 50th of a bike, which is nothing. So they're able every day to almost perfectly predict bike demand. That sounds like overfitting to me, or it sounds like a transformation was done and it wasn't untransformed. So that's where I get really, I'm like, oh, let me look at this. Let me look at this. Let me see how the predictions came out. So I get a little worried. We're gonna get project 2 up and going right here. But if you have questions, let me know. We're doing some lab in 474 today. And project 2, chapter 17. Great job, Jessica. Was it Jessica? Chapter 17, not due for a few days. Doing some great work right there. Okay, let's go put a note right here and start the project talk. Thrifted on stats 1, project 2. Here we go. Okay, so if you get project 2 turned in early, you can get 8 points bonus. Now, I want to put this warning out here. Good to see you here, Jessica. I want to put this warning out here. Don't do the project early just to get the bonus. I've had people turn in really lackluster projects. Yay! Good to see you, Jessica. I've had people turn in really lackluster projects. And I mean, people turn in great projects and get 108. That's awesome. That's what I want to see. But I've had people be like, I just remember one person emailed me and they're like, I wanted to get the bonus, so I turned the project in early. Is that okay? And I was like, yeah, of course. And then they turned it in later today, probably around maybe 2-3 hours after class, getting it finished up. Good question right there. So it'll be Sunday. The last assignment is due Sunday. So it'll be put out later today. But make sure if you're turning in the project, you feel good about it. You've asked questions if you have them. You turn in a good, strong project, and you don't just turn it in to get the project in. I think most people do that, like turn in a good project, but I just felt so bad for the one student that got like a 68 because they got like a 60 plus 8. And I was like, if you wait and we look over it. Okay, so let's take a look right here. We got the instructions right here. We love instructions. We got the data right here. We love data. We got documentation, which tells us about the variables. Awesome. We got a help video, and I'm currently doing, am I wearing a Rick and Morty shirt right there? Nope. I'm wearing my Nightwing shirt that lost Nightwing after I washed it like 3 times. It was a really cool shirt. Now it just looks like a great t-shirt. Actually, oh no, that's my New York t-shirt. Anyways. Okay, let's open up some files right here and take a look at the documentation. I like soft t-shirts. That's what I have. Got a rotation. So here we go. Enable editing project 2 instructions. Okay. So when you do your project, 474 probably knows this pretty well. You will need to start your project with a what and end your project with a what. What will you need at the start of your project and at the end of your project? What will you need at the start and the end of your project? Oh, surely someone knows. What do you need at the start of it? What do you need at the end of it? Start with an executive summary. Kirsten, you got it right there. Now, an executive summary, someone said it yesterday. They said about 5 to 10% of the length of the project. I think that's pretty good. I think you should go for at least like half a page. And your executive summary should have the following components. Introduce the reader to what's going on. Give a summary of your results throughout the projects with numeric backing. And last but not least, give the action items. So this is about how it will look. We've got here intro to like what's going on, who are we, what are we researching. Make sure to mention what the company is, what we're researching, maybe what our goals are. And these are findings, but make sure you give the numbers, findings with numbers, and then action items. Please tell me if you think the grader is not fair. 201, I have a grader, which is so nice. Huge shout outs to the grader. And you see the rubric right here. Take a look right here. Action item right here outlines what is being researched. That's your introduction. Important results. And then if you don't give the numeric backing, you get 2 out of 5 points. So you can see right there on the screen, it says that you didn't give enough numeric backing right there. So you get 2 out of 5 points. You don't want to fall into that category. If you read through these right here, it should give you a good idea of what you're looking for. And if you don't feel you're graded properly, you can always say, hey, Brian, I feel like I should have got those 5. I can agree or disagree with the grader. I've definitely changed grades when I'm like, yeah, let's give you. And I really am against the grader clicking the too long button. Frankly, if you see this button clicked, unless you gave like a whole page executive summary for like a 3-page report, then I might be like, well, yeah, we could have condensed that down. It is a summary. So rarely do I agree with like taking points off for too much, but it is an executive summary. So we do try to summarize. Last but not least, the action item here, and that's what we're going to do from the report. You think of action item like, we will do this. This is the action we are taking. So action item is clear and connected to the report, 5 out of 5 points. 15 points of the project right here. Now, here's the interesting thing. When do we write the executive summary? So you can't do this right now. When do you write an executive summary? Who knows in the chat? When do you write an executive summary? So remember, this is a summary of your report. So when you think about when you write the executive summary, you write it last, Kirsten. Yep, you write the executive summary last. So you write it after you do everything. Great to see you here, Sierra, too, and you write it last. Also, you have at the end of it the future research, which is its own thing. 10 points right here. Now, the future research, which goes at the end of your project, is like a brainstorming session. It's like, let's think of cool new ideas. Is that going to ever let me get beyond it? It's never happening. What's this? Haha. Okay, so future research is going to look something could be a little smaller than that. And I'm doing this a different color because this is a different thing. This is like new ideas. This is things that go beyond. These are your ideas which you could do after the project. Like not with the results in the project, but where do we go from here? We've looked into this. Well, maybe we could do future things with this, this, this. I think about a third of a page is good on it. You don't want to just do like 2 sentences. Let's take a look at what the future research is graded on again. Future research is clear and also connected to the report. Now, connected to the report doesn't mean you go back through the results. This is not a re-summary of the results. You don't just go and say, well, we looked into this and we found this and we found this and we did this. It's not a summary of everything at the end. That's the executive summary, which is summarizing your full report. The future research is new ideas. In the report, we looked at this, but we could probably look into this into the future, new variables such as blah, 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 or, it'd be really interesting if we got some time to do blah, 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 blah. It's things you haven't done yet. Neatness, please make sure your graphics look neat. We've actually already covered 30 points so far of the project. Now, let me take one of the tasks right here. I think I do all the tasks in the video. Here's project 1 sample T. So if you're looking for one, let me ask you, who's doing the project right now? If you're doing the project, I want you to ask, well, which one would you like to do? Because I do them in the video, but which one would you like help on? You can see we got 1 proportion Z right here in the video. So I walked through the 1 proportion Z. There's some Josiah Wilkinson. I walked through the 1 sample T. Which one would you like to hear about if you're here right now for the project? So we can put, let me write this, project 2, executive, summary, and future research. What would you like to hear about the project? Is there a certain portion you're working on? We could walk through it. Just be like, this part of the project, like the 1 sample T, the 1 sample Z, we got here the 2 sample T, I think at the end, the 2 sample T. Which one of those would you like to hear about? Let me know. We could go over to some chapter 17. The video walks through all of them. Maybe that's why people are like, I'm fine. Yeah, the 2 sample T, that's really great. Oh, and that's chapter 17. Jessica. Oh, Meath and Jessica both want 2 sample T. So yeah, that's of course. Here, we'll put on our nice chill music. Yeah, chapter 17, 2 sample T. Okay. Let me take a note right here. Stat 201, project 2, 2 sample T. And 12. Okay, let's do a 2 sample T. Let me get some data going up here. Let me draw my pen. Okay, so I'm not going to do your exact data, but I'm going to go through the questions with a different data set. Let me get jump loaded up. I got to get the new jump license too. Still working with the jump that works currently. They're going to put out jump 17 soon. Okay, jump is opening up. Let me get some data up. And here we go. Let's talk about the 2 sample T. When we do a 2 sample T, what are we doing? 2 sample T is chapter 17. If we do a 2 sample T, what are we doing? The 2 sample T. Okay, so what does T mean? If we see T, what does this mean? The T means the Y variable of interest is what? The T means the Y variable of interest. I'm going to draw a graphic right here to maybe help you out. Great job, Meath. Wow, excellent work. It means the Y variable interest. That's worth 500 points, Meath. I thought I was going to have to help out. 500 points, Meath. Excellent work. You are right. The Y variable of interest is quantitative because Mr. T is mean. I'm sure he's a nice guy. 475 Shreya, definitely. We'll do that here in a little bit. Yeah. So does anyone know what graphic this is? This is what you see for a 2 sample T test. You have like yes and no, and then you have something like, let's say grade. Like, did you go to the Kahoot review, which we're going to do this weekend? So this is grade. Did you go to the Kahoot review? And we can compare right here. So what graphic is this? What graphic is this? This would be what 2 sample T graphic right here that we often see. So what is this? It's a side-by-side box plots. Nice job, Jessica, right there. Side-by-side box plots. So compares the mean for 2 groups. So that's why we call it the 2 sample. The 2 sample right there means we have 2 samples, 2 groups. So 2 groups is the 2 samples. And then the mean portion right there, as Meath pointed out, is the T part. The T is what William Gossett made. It's a distribution to compare quantitative values. So you can see here the 2 sample T compares the mean for 2 groups. We just need to know how to decode this. And so with this right here, we're going to make a side-by-side box plot, and we're going to compare the mean for 2 groups. So the X variable has to be what? Meath said that the Y is quantitative, so we have a quantitative Y, and then the X variable has to be a 2-level what X. So the X has to be a 2-level, so X needs to be a 2-level what type of variable for the 2 sample T. Because I think we need to compare the quantitative measure to 2 groups. So X is a 2-level, so that's keyword we use in like 474, 320 levels of this variable. not a factor. You could say, right? Categorical, Kirsten got it right there. Yep. Categorical variable, yep. So the 2 sample t compares the mean to 2 different groups. It's just going to say, let's compare the mean to this group. Let's compare the mean to this group. What is the null hypothesis? Now, this is a really good stat tool. One language. Basically, null hypothesis means our initial belief. And the initial belief is that the mean for group 1 minus the mean for group 2 is equal to 0. Now, if you algebra this, if you take that in algebra, it's just mu1 equals mu2. So what are we saying about the difference right here? We're saying that there is what difference? And then we could pick an alternative, like mu1 minus mu2 not equal 0. The sign of the alternative is based on the question. But we're saying what between the 2 groups? Like, hypothetically speaking, we believe right now there is what difference between the 2 groups. And technically, you can test any value you want, but usually we test a value of 0. Hey, Michelle, good to see you. We're saying there is no difference. And that is a value you can change right there. Great job. Yep. We're saying there is no difference, which because we can math it like this and say that they're equal to each other, which means there's no difference. So this is what we're testing right here. Like, think of a crazy question I could do. Could I test to see if males and females are there? Oh, darn it. We used to have height and weight on this. Oh, let's do it. Let's do this. I want to see if there is a what between what's and what's. I want to see. So look at the question. Look at the columns. I'm going to put gender here in the X. And then I'm going to put in the Y variable of interest, high school GPA. So what am I asking right here? Just think about how I'm asking this question. I want to see if gender explains high school GPA. And sorry, guys, I think I didn't help this data out very much. You'll see shortly. So I want to see if what? Like, phrase this like, Brian is investigating, statistically speaking, is if there is a difference. Jessica, good. So correlation is only between 2 quantitative variables. Jessica, let's throw some 500 points. Correlation is only between 2 quantitative variables, but we can always say association. Association is the global term for whenever we talk about 2 variables. We can say, is there an association between like any of these variables? But if we say correlation, then correlation would be between 2 quantitative variables right there. Yeah, so you can say association or relationship, but as soon as you say correlation, it's a quantitative relationship. There is technically a way with indicator variables to make it correlated though, but then it would just be binary operators. So we would say, is there an association between somebody's gender and their high school GPA? Now, we can put the side-by-side box plots here with quantiles. Makes it look a little bit nice. You can add that to yours. And then we can do the t-test right here. And let's zoom in on this. So you might already be able to see it. Guys, a little lower, guys. And then let's go here to the t-test right here. And so let's think about what these results mean. Okay. This looks like a bunch of complicated output, but we're going to break it down. Well, let me do this. Don't do this for your assignment. Don't click. Well, no, you can click that. That's fine. Okay. You could add this if you want. Tell me about males' GPAs. Just do 2 decimals. What is the male GPA? What are males' GPAs? You can add this if you want. What are males' GPA? Just look at it and be like, males had an average GPA of this. I think this will help with understanding the question. Males had an average GPA of, well, not quite 3.8. Sorry, guys. I wish I had this. Good job, Meath, right there. Not quite 3.8. 3.72 males. So that says males. There were 355 males. They had an average GPA of 3.72. And the standard deviation. We don't have to worry so much about the standard deviation. Females had a GPA of 3.87 on average. So what do you think this difference is? You see male minus female. What do you think that difference is right there? And how is that difference being calculated? So, yeah. Woohoo, I wish I had that. I did not help with this GPA thing. How do you think we're calculating this difference right here to get negative 1.4985? We're taking the difference between the 2. That's what it is. That's what the difference between 2 means is. We're going to take the difference. Great job. Just great. Yeah, that's exactly it. It's the difference between the 2 means because that's what we're analyzing. And so I hope people have like a, oh, moment. We're analyzing the difference between 2 means. So let's take the difference between the 2 means. And there it is right there. I might not have carried all the decimals. So once we take the difference between the 2 means, what if I told you 2 things have a difference in price of $50? Would that be a lot? Yes or no? And outthink my question. I tell you two things have a difference in price of $50. Would that be a lot? What are your thoughts on that? Because we got the difference right here. We know what the difference is. And then we have to ask, is that a big difference? So would a difference of $50 be a lot? Just think over why I ask it this way, because I want you to question me. Is a difference of 50 a lot? Is it? $50. Is that a lot? Is that a big difference? Boom, Meath. Meath is, both of you are destroying everyone right there. 500 points, all of you. Yes, it depends. I tell you that a house and another house have a difference of $50. You'd be like, $50 is nothing for a house. If I tell you two candy bars differ by $50, you'd be like, what is that candy bar made of? Gold? Like, why would two candy bars differ by $50? What's going on right here? Is this some rare candy bar? So what do we need to do anytime we have a difference? If we were to take the difference between two sample means right here, what would we do to that difference? Just like when we take the difference between a proportion and a hypothesized proportion, we do this to it. These are the other chapters. This is not our current chapter. That's a z-score. Or we take the difference from a sample mean to a hypothesized mean. We do this to it. So we always standardize it. Michelle, 100 points right there. Great job. So we need to standardize this difference. The bottom equation right here is s sub 1 squared over n sub 1 square root plus s sub 2 squared over n sub 2. And the bottom portion of all these are how you standardize a difference. So all of these right here are how you standardize a difference. But here's an important thing to know. With this equation that we're using, the top part is always the difference. And then the bottom part is always the standardization. So we always get a difference. And then in this instance, we have what is called a standard error. Do you see on the screen currently the standard error right there? So here's the difference, and here's the standard error. Difference, standard error. If you get these two numbers and you divide them, you'll get the what? So we will get the t. The difference in the, the standard error of the difference is it right there. That's it. That's the standard error of the difference. And there it is right there. So that's the difference divided by the standard error. And take a look. Watch on the screen right here as we take the difference of 0.49, 4985. Wait. 0.4985 negative divided by 0.02770. Boom. T statistic. So that is the t statistic right there, and a t statistic is a standardized difference. So now, think about this. If I told you a z-score, we only got a few more questions on this, and we're going to look at answering every question on the project with this. If I told you a z-score was -5, would that be large, Jessica and Meath, and everyone? Got Jessica, Meath, Sam, everyone here. Would that be large? If I told you a z-score was -5, like 1, 2, 3, 4, 5. If I told you it was -5, would that be large? Yeah, that's ridiculous, right? That's way off the curve. That's insane. Great job, Kirsten, Jessica, and everyone. That's crazy. So we landed all the way down there. And take a look at what you see over here on the graphics. It shows you it right here. This is it showing you where you landed. That little image I just drew a second ago, a little tiny sketch right here of this. Actually, I might not have done too bad today on my little sketch. There's my sketch, and there's their drawing, and I said we landed 1, 2, 3, 4, 5, 5.4 technically, so we're actually a little bit even further over here at -5.4, and that's what I drew right there. We're way off the curve. And if you're way off the curve, a lot of your p-values are going to be very, very what? Because this is very unlikely. So less than this is like none of the curve. Greater than it is the whole curve, and double nothing is still basically nothing. So if you're down here on the end of the curve, you often get very what p-values because you're way far away. If you're down here at the very bottom of the curve, you usually get very, very close to 0 p-values because this is basically impossible. So last thing we can talk about right here after we just did the p-values, degrees of freedom are a complex formula for the two sample t. We like to say The one sample t is n minus 1. The two sample t is a too complicated formula. Let me just show that right here. The two sample t, we do not ask you to know this on the test. The two sample t degrees of freedom formula is, so they're showing it right here. Let me copy this. Copy image. Okay. So the two sample t degrees of freedom formula is the equation right there. They're using X bar up there, but we won't solve for the two sample t degrees of freedom. We'll use applets. I've got the TDF calculator on here to solve it if you need to solve for the t degrees of freedom for two sample t. Good to see you here, Noah. And the one sample t degrees of freedom would be a t is equal to y bar minus mu naught s over square root of n. And degrees of freedom for this are what? For the one sample t, the degrees of freedom are what? Good practice right here. Then we're going to solve all the project questions right here after we understand the theory. The one sample t degrees of freedom, n minus 1, boom, nice and easy, right? And so the one sample t has one mean that we're testing, and the two sample t has two means. There's two means, there's one mean. So you see how it's mean one. They're just using x bar, which is the mean of the variable x. They're just calling the variable x. But great job, Lauren, right there. Lauren, good to see you. 100 points extra. So we see here the one sample t and the two sample t. And remember, the t is for quantitative variables when we're doing the mean. Oh, yeah, let's go ahead and look at the question specifically to see what it's asking. And here, let's go look at the project. I'm going to do this like it's the project. So now that we know the theory, the two sample t test. Let's make sure we answer each one of these. Perform a two sample t test. Analyze the difference of two means using an alpha level of your own choice. So alpha is the point at which we what? So I might even say to the reader, I have picked an alpha level of what? Alpha is usually equal to what? And what does alpha tell us? You could probably pick the classic alpha. But what's the point of alpha? It's usually, great job, Jessica, right there. It's usually equal to 0.05. And it's just a bar that... Yeah, Lex is talking. I was like, who's talking in the main room? 1 second. Alexa started playing music. I was like, I started to hear someone talk in the main room, and I was like, what's that? Living in a modern world. If you are below alpha, you reject. And if you're above alpha, you fail to reject the null. Which don't say accept. Don't say accept. We don't accept the null. You either reject the null or fail to reject the null. So we're going to specify our alpha right here. Clearly explain to the reader the point of the test you're performing, why it's important to the company. Okay, so my company works on helping students who need additional tutoring. And we want to see if maybe males, like who should we hire as tutors and who should we reach out to more? So we're trying to look at GPA. Does this make sense when I'm saying like my company looks at people and their tutoring needs? So we're wondering who we should maybe email more about hiring and try to reach out to more. See, they're not going to hire me, are they? So we're going to maybe, I don't know, maybe we'll go to sororities and stuff and say, hey, you know, would you like to maybe be a tutor? I don't know. I don't know how we'll use this, but we'll somehow find a way. But we can just write whatever you think, whatever you want. Once again, I would have wished I had a 3.72 GPA in high school. I'm the outlier in this distribution. So with that right there, we want to help students in need, and we want to find students with higher GPAs. So that's where we're going to do this analysis right here to see if GPA can be explained by gender. So what have I done right there? I have done what? Just explain it. That whole thing I just did right there. What did I just do? Explain. So I just talked a whole bunch right there. You can't write down what I'm saying because I'm doing a different project, but I am doing what right now? I just did what? Like, why did I say, oh, we're going to analyze GPA and gender to see if maybe there's some association where maybe males or females have higher GPAs. Thus, we want to reach out to the people with high GPAs so that they can be tutors. And we want to reach out to the people with lower GPAs to maybe see if they can get some help tutoring. So this might help us make decisions. What am I doing right there with like a sentence or two? What am I doing? Like, think about each one of these as a thing you need to do right here. So I'm clearly explaining to the reader the point of why I'm doing this. I'm saying, like, here is why I am doing this. This is why we are reaching out, or this is why we're doing this analysis. This analysis is going to help us make decisions about who to reach out to get as tutors and who to reach out to get to ask if they need tutoring help. So make sure that's clear. Make sure to write 2-ish sentences. It all varies. Now, here's a harder part. You ready? Without using statistical notation, explain the null and alternative hypothesis for the does not equals test. So we could do this pretty easily. What does anyone know what the null hypothesis is for this test just in words? The blank of blank and blanks is blank. I'm going to help you out right here so you can fill in the blanks. The blank of blank and blanks is blank. The null hypothesis would say what? Or you could say, kind of, very close, Meath. So I should have put more blanks there. Very, very close. And very, very close, Jessica. Kind of. So think about how it is in statistical notation. In statistical notation, I thought we wrote out the statistical notation earlier. Here it is. It's mu1 minus mu2 equals 0. Mu1 is the true mean. Does that make sense? Like the true mean for males minus the true mean for females is equal to 0. So you could say the true mean for males equals the true mean for females, which equates to. So let's try to do what I saw right here. The true mean GPA for males and the true mean GPA for females is equal. Or there is no difference between the true mean GPAs of males and females. Does that make sense to say right here? The difference between the true... Yes, Shreya right there. Nice work. Yep. Because those are true means. Like, there really is no difference. Or, like, I don't know if I'd say it like this. The reality of the world is that there is no real difference between the average male GPA and average female GPA. That's how we might talk statistically, but not so statistically. The reality of the world, like the truth, like in reality, there really is no difference between the average GPA of a male and the average GPA of a female. That's what the null hypothesis could maybe be like. If you talk about like, well, you know, if we were to have all the data, then we would probably see there really is no difference. Like the reality of the world with all the observations, all the data, mu, the true mean. That's one way to talk about it. Now, the alternative would be there's what? We are looking for what? We are investigating to see if they're, because we're doing the does not equals test. So we're seeing if they don't equal each other. So we are investigating to see if there's what? To see if there is a difference. That's what we're saying. The reality of the world, like our starting assumption, we could say this. We should say our starting assumption is that there we go. So that's what the null hypothesis. Like we start out with an initial belief that there is no difference between the average GPA of males and the average GPA of females. We're investigating to see if there is evidence of a difference. Evidence is a good word for alternative. It's really powerful right there. So our starting assumption is that there is no real difference between average male GPA and average female GPA. We are investigating to see if there is evidence of a difference. Bunny's in the chat. So good stuff right there. Explain the null hypothesis and alternative, does not equals test. Finally, explain the conclusion your company makes about the test and how they arrived at their decision using the confidence interval. Now, that's interesting. Now, I want you to look at the confidence interval. If there is no difference, what would be in the confidence interval? Let me just take the output from it. If there is no difference, what value would be in the confidence interval? And hint, you can look to see how the test was set up. If there is no difference, what value would be in the confidence interval? If there is no difference, what value would be in the confidence interval? Like if there is no difference. If there was no difference between males and females, then we'd say like, it's possible that this is the truth. It's rather interesting what the difference is here. If there is no difference, then what would be the value in the confidence interval that should be there? If there's no difference. If there was no difference, what value should be in the confidence interval? If there's no difference between the means, then a possible hypothetical true value should be 0. Yeah, that's it. Yeah. No difference. It's 0. 0 difference. Think about how you would interpret this. Now, I'm going to make this easy on you. Don't go all statistically here. Just do it like we didn't learn stats, that should be the theme of this class. Pretend you don't know statistics. Tell me about females GPA, average female GPA to average male GPA. If I change it to look like this right here, and I want you to think about the way this equation is written, then tell me, it looks like females, blah, 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 blah. So compared males and females, it looks to be, I changed the numbers to make them super nice and neat. So you'd say, well, maybe females are about, what do you think? Now be careful, it is male minus female. So remember, it has to be male minus female, which means the female GPA was higher because it's doing math like 8 minus 10, hence we get a negative value. Negative interval, negative values means the second quantity was larger. It's not 8 minus 10, but just showing because the interval is negative, it implies that we have evidence the second mean is higher. So what would this be right here? How would you interpret this? It looks to me that what? It looks to me that the female GPA, the true female GPA, is somewhere between blank to male GPA. The true female GPA is somewhere between blank to male GPA. So that's what the confidence interval is telling you. It's your estimate of the difference between the means. You're trying to understand the difference between the means, and the confidence interval is giving you a confidence interval to estimate the difference. So that's an upper for the difference and a lower for the difference, saying difference between the means is probably about this to this. So how would that sound? Like you could say, I am 95% confident. The true difference between male and female's GPAs is that the female GPA is somewhere between, let's see what people say. We'll give it a second longer here. So I'm always hoping people have that moment where they're like, it makes sense. I see it. I understand what this output means now. Because it's a lot of numbers. If you don't know what the numbers means, it's like, this is just random stat stuff. So are you ready? I'll do it in 5 seconds. So I am 95% confident, give your confidence level, that the true difference between male and female GPA, because that's what we're analyzing right there, is contained in the interval -0.1 to -0.2, implying that we have evidence that females' GPAs are somewhere between a 1/10 of a point to 2/10 of points higher than male GPAs. So it seems to me, if I talk, like I'm not a stats person, I might say, it seems to me like maybe females have an average GPA that's about a 1/10 of a point to 2/10 of points higher than males. Does that make sense to say that? Stat tool 1, does that make sense? If I say, it seems maybe that females have about a 1/10 of a point higher to 2/10 of points higher GPA on average than males. It's probably, they're a little bit higher, 1/10 to 2/10 of a point, somewhere, maybe about there. I don't know what the true difference is, but they're a little bit higher. That makes sense? Awesome. And so think about this. 0 is not in the interval. So if you were to do a statistical test on this, you would reject the null. And this is the does not equals alternative right here. That's the does not equals alternative, and you would reject the null. This is the greater than alternative p-value. This is the less than. There is not evidence that males have a GPA greater than females. There is evidence that males have a GPA less than females right here. That's you could have done that test. We didn't say to do it. We said do the does not equals test, and there is evidence that the GPAs are not equal to each other. So one last question right here. What is the margin of error of this interval? I rewrote it, but see if you can tell me the margin of error, and I'm going to draw it down here, and then we're going to switch topics. See if you can tell me the margin of error as I help you see the interval. What is the margin of error of this interval? Should be reversed, actually. Nice job, Meath. Yep, that's right. Great job. Yep. Good practice right there, knowing how to get the margin of error. The margin of error is half the length of the interval. So I changed the numbers a little bit here so we could see it. And yeah, we would conclude we have evidence of a difference right here. That's the two-sample T. So Jessica and Meath, does this make more sense? We would conclude there is evidence of a difference, and the difference is somewhere between the average GPA of females being about being about 0.1 to 0.2 higher. Question, I wanted to work on my lab. My R froze. I can't click on any files types. Did it happen after the market basket? Using his try restarting, and my usage is only 37%. So we might have to meet. One student had that they had so many things open in their global environment that it was crashing their R. They had I think they had rules that were so huge. So you might need to, we had to like stop their rules from loading in, stop their global environment, stop it from reloading the global environment. And yeah, happened yesterday after I finished the report 6. We might have to meet, and I might have to look at it because I was able to get that students fixed. They had everything loading in their global environment. What you want to do, let me see what I have open in R right now. And then we're going to do some more work right here. Let me open a new one titled. Okay, so if you can, as quick as possible, if you get inside of R, you want to clear those MIBigos. You want to clear the global environment right here, if possible, right there. Clear the global environment, and that can probably help. If R is crashing, it might be doing too much. You might have a bunch of things stored. I'm trying to think what you would have stored from. I got that cleared, and it's not helping. Like, that's currently cleared, and it's crashing still. That was the last time. I probably have to take a look at it because that's the last time. The student had it crashing after they were doing market basket analytics because they had like a rule set with like 2 billion rules in it or something. So yeah, Sydney, let me know. Message me, and we'll try to hop. I've got a meeting right after class. And we'll try to hop right in, and we'll try to do it. Trey, I think we're doing your question next, and Jessica, we're going to do the other one with the man goes to 2 cities, 2 sample T by hand. Okay, let's do some 475. Awesome. Thank you, Sydney. We'll get this figured out. Great work, everybody. I know Shreya and I think Noah, we were both talking about how quick everything is. Jessica, great work. I'm so happy that we do this because, as I said at the start, I want to see all my 201 students, and it's just great. I'm so happy. Meath is here, and Jessica. Just really great seeing all the 201s here. Knox, good to see you, Knox. Let's hop over and talk a little 475, then we'll go back to 201 here in a moment. 475 coming right up. Let's do some R coding. Here we go. Meath getting a ton of points right there. Great job, Meath. Okay. So Shreya, you were wondering about the time series cross-validation with the stretch Tisbol, right? So let's do time series cross-validation stretched Tisbol. Okay. So one thing to know is that when we make a stretched Tisbol, let's go grab some data. Library FPP3. So this is our forecasting principles and practices, something, how we do our forecasting. Let's go grab some OS data, and let's go grab the airline passengers. And these are how many airline passengers there have been every year. Now, this data is not what? Think of an S word. It's yearly data, so we're actually, in a good way, maybe limiting our choices on models. I worked on yesterday and compared the model, but you saw a huge difference. I want to make sure. Yeah. The difference we saw. Yeah. Let me talk about that because I know we talked about that via Discord. So this is not seasonal. Boom, Shreya knows it right there because it's just yearly data, which is pro and con. First thing you want to do is probably do what? If we have this right here, I'm not telling you what to do. Like, just pretend you get data. You look at this way. Now what you do? So there's no filters on this. We could filter by year. Good answers right there. We could filter it, but this just has year and passenger. So what should we do now? What should we do now? Plot it. Look at it. Boom. There you go. Definitely got a strong what in this data. Definitely got a strong what in this data. There's that. Whoa. Definitely a strong trend. Now, let me ask you. We love this trick question. Great job, Sierra, right there, and great job, Shreya. We do this trick question all the time. Your graphic looks like... I can't get it the way I want it. Sure. Your graphic looks like this. Your graphic looks like this. Is this positively or negatively autocorrelated? Your graphic looks like this. It's all blurry. Positive, we can't trick Shreya right there because it follows itself, right? Positively autocorrelated. Now it does have a negative correlation with time if that's the time axis, because you might say, well, it's going down, that's negative correlation. But it's positively autocorrelated because it follows itself. And can't trick Shreya right there. Shreya, 500 points. You're like, I know this. Brian, you've drilled us on this. Sometimes 50% gets it wrong during class, and I get afraid, though. That is positively autocorrelated. Autocorrelation is self-correlation. And we can check this right here if we just go grab some ACF and we look at the ACF for this, and you can see the strong positive autocorrelation. We also see the decreasing right here showing a trend. So when you have strong positive autocorrelation, I messed up playing time. You're like, I can get this now. Okay, so we know what's kind of going on with this data. We got some strong positive autocorrelation. Can we just go and difference this? What's it called? We'd probably need to take and difference, right? Okay, that's Tisbel one. There's the differencing of it. And can we do... I'm always wondering how to do things. Nope, doesn't like that. We might have to do ACF of the differenced passengers. And this will detrend it. Okay, that did it. Okay. And then... yeah, that's some good residuals. These are good residuals because nothing is what? These are good residuals because nothing is what? And Shreya, if you're following along, you understand these plots. Like, when I see this, I look at it and say, that's good residuals because why? Nothing significant. Boom. Sierra knows it. 2. Great job, Sierra, following along. 2. Nothing is statistically significant. Nothing is out of bounds. This would be statistically significant. It's interesting because you might think, well, wait, don't we want things to be statistically significant? That means there's some signal we didn't catch. If something is statistically significant, there is significant autocorrelation at lag, whatever, and that means we didn't take that signal and hold on to it and use it to explain the model. So we want to find the signal in the noise and or take the signal out of the noise and leave the noise. So let's go ahead and make a model right here. We're just going to make simple models. Okay, let's go ahead and just do the naive model. About as easy as it gets. The naive is going to do the last point forward. Can't say that word. There's the naive. And let's go here to fit forecast. That's what I was thinking about. Forecast, and we're only forecasting that. Let's forecast 12. There we go, 12 forecast. Let's go here to fit. And with fit, let's go to auto plot. And if you add the original series, you get, oh no, oh. There we go. There is the plot right there. Thank you, Shreya, watching the code as we do it. Excellent work. So there is the series auto plotter right there. We can make it look all fancy. We'll do that later. But now we have a model. And you know what? This is not such a bad model. I should be able to do... Sometimes I have to cheat and look for the code. But if you look at this right here, the way it's going, what model might you suggest? Last question before we do a stretch Tisbel on this. What model might you suggest? The mean model is not a great idea. The drift, yeah, sure, you're getting it. It looks like it's just, if we do the drift model from first to last point, we probably get a much better model. Then we maybe will look at the cross-validation on that. That's probably going to come out a lot better. So the drift model is, let's go here and go drift. I have to remember a lot of these because is it, no, it's RW. Is that it? I might cheat and look at the book. Random walk models. Here it is right here. There it is right there. So it's RW, and then you have to add the drift as a, so it's a tilde. Okay, so we need to do, what's the name of the variable again? Passengers, is it? No, it's not ACF. It's passengers. Okay. So passengers, tilde, drift. You make the formula. There we go. And there's our models. There's our models. And we can remove the confidence intervals if we go to, it's like right here, is it not? No. I always forget. Yeah, not bad, right? Here we can remove the naive model for the time being. I always forget the, is it autoplot level? My gosh. Sierra just rocking a good job right there. It's autoplot. Under the autoplot, level equals, oops. So level equals null inside of here. There it is right there. And there you go. Yep. There you go. That's got it. About 1 billion things we can do. So we're just looking at the forecast right now. No confidence intervals. Might worry more about our final models later on, but there it is right there. There's our 2 models. And let me just ask this. This is what I feel like with these codes and being able to make so many models. It makes me feel just really powerful. It makes me feel like I can just like make models, make forecasts just instantaneously so quickly. So hopefully you're starting to feel that way. It's like, oh, you can just go through this process of making models very fluidly and make a ton of models. So the drift does look way better. And let's go and do the stretch Tisbol. Dun, dun, dun. And Sierra, we're probably going to grab that awesome cable code. Thank you, Sierra, for dropping cables, which I had heard of before, and I just haven't used nearly enough. The cables are some really awesome tables. Don't even know why they call them cables, but they're better tables. Let's check them out here in a moment. Okay. We got a really pretty one right here. Make 4 in one graph and copy paste and do that. Oh, because, well, yeah. Oh my gosh, you can do auto layer and so many things. It's pretty crazy what you can do with ggplots. Okay, so now we need to make a stretch Tisbol. Let's take, go to stretch Tisbol. It's going to take that. And let's go here to initiate. Wait. Dot initiate. This is where it's going to start stretching it at. What? Lost passengers. It's, I want to see it up there. 47 observations. Let's start it on 3. Is it dot step? Why do they do that? Why do they do that? Let's step it by 1. There it is. So the stretch Tisbol is not going to take up too much memory. Let's go to, and let's call it stretch. Sure. And there it is right there. There's our OS passenger stretch. So the stretch Tisbol takes your data, and let's look at it real briefly right here, and it stretches it starting by how much you want to initiate on, 3 points. You get 0.1, 0.2, 0.3, look like 70, 71, 72, 70, 71, 72, 73, 70, 71, 72, 73, 74, and you keep stretching it by how much you do a step forward each time. So if you look at, if we go to step 2, you can take a look, you get a lot less data. And if you look, each time you're stretching it by 2, does that make sense? You initiate on 3, so that's what the initiate means right there. You're initializing 3 points, and then the step right here is the step forward each time, that now the next time instead of 3, we have how many observations in the data frame. Makes sense? Nice job. We have 5, so we're stepping it forward by that much. We did some visualizations on this, and the book has great visualizations too. So the question becomes, well, what do you want to initialize on? What do you want to step by? In truth, it depends on how big the data is. This data, there's no problem with it. But if you were to go to something like, let's go, no. Good. Okay, so watch this. what's going to be the problem with creating this model right here? I want you to look at this right here. Just take a look at this. This is the stretch Tisbol for the os livestock. So what's going to be some of the issue right here? Just look at that. That's the stretch Tisbol, and look at that. I think Shrey sees it, right? So this takes up a lot of memory, and if you're making a model on this, it's going to be pretty crazy. So I'm actually going to remove that. You just want to make sure you look at the size of the object you're creating. That's going to create some problems. It's going to be a lot of observations, a lot of predictions, a lot of mathematics that's just going to really wreck your computer. So don't do that. Don't do that. Okay. So we're going to do the same process right here of making a model. We're going to make it on the stretch Tisbol now. And we should get the fits right there. Looks good. Oh, we should have called it fit 2. Fit 1, fit 2. Do I have my code in order? I think I do. Fit 2 did not run. Fit 2 did run. We have fit 2 created right there. So we have fit 1 and fit 2. Yeah, that's all the fitted values. Cool. Okay. Now I'm always double checking. Definitely takes crazy longer to run, doesn't it? I'm always double checking. Let me go grab the exact code because I think we've done everything properly. And let's go grab the exact code for the time series cross validation. And there it is right here. So we did the stretch Tisbol. Relocate just moves the columns, so we don't need to do that. We've got right here the model being created, the forecast, and then we're just running it in accuracy. So we could just take and do the accuracy, and we should get that right here. But here's a big thing. We can then compare it to the training set, which is what we need to do right here. So this is going to be, let's take our fit 2, pipe it into, I think I already did the pipe, there we go. And we don't want to do that. We want to go to the original data set. Yeah. And that's fine. Don't worry that it did this. Now, if you look, these are all the test data right here, right? So this is all of my information right here with the test data versus the 2 models. Shreya, does this make all sense what you see on the screen right here? Does everything make all sense right here? And I think if we go and go select, yeah, because I'll select the columns. Dot model, dot type, unused arguments. Let me go. Oh, it doesn't like that for Tisbols or accuracy tables. Makes sense. Awesome. I might cheat with this a little bit because I might just call this df1. Sometimes I work better with data frames. And if I go here to the data frame, I could just literally go and select dot model. As long as you know one way to do things, rows, columns, dot type, and RMSE, and let's grab Rob's favorite right here, MASE. There we go. Oops, what did we not grab properly? Oh, really? There we go. There we go. So now we've got the model, the type, all this good stuff right here. So now we just need what here? What else would we need, Shreya? We got the RMSE. We've got the MASE. What else do we need right here? We've got it, how it does on the test data. So what else would we need now? We have how it does on the test data. So that's the test data because we took the fit from the stretch Tisbol and we saw how it did on the original data. So this is how it does on the test data. This is the cross validation. That's what that is. Good to see pause in the chat. We could do row names. Did I do row names for that? We could. Probably what I would do. So this is the time series cross validation, Noah. This is the time series cross validation. We want to go and get the original fit and see how that does. And we could go right here and go to the fit 1. Maybe I should have called this. Here we can do fit 1 and do this, and then do fit 2 and do this, and store this into fit 2. Oh no! Is fit 1 not doing its thing? There's fit 1. Accuracy. What? The future data set is incomplete. Out of sample data set, we'll be testing 12 observations are missing from 2017. And oh, what's going on? What's going on? Let me see right here. We should be able to get the accuracy. Why are we not getting the accuracy, Shreya? What is going on? We should be able to get our accuracy for the initial data. And the accuracy for the initial data, because he combines his right here. That's where it confused me in the book, because he doesn't do it. So here is his stretch Tisbol. Seeing how it's doing. Oh, you know what it is? When you do it on the original data set, you don't put that there. Really? Data is missing with no keys. Let me double check. We're so close. Oh, you don't forecast it. Really? Really? Yeah, because it doesn't have the answers, so that makes sense. Okay, so we need to go back here to our model. And right here, to get it for the first part, need to go right here and do accuracy on this. There we go. There it is. Oof. Shreya, we're hitting the same thing you saw last night. Yeah, forecast actually hates each other. So what it is with the stretch Tisbol, you know the answers, because on a stretch Tisbol, you're stretching it out each time and you have the answers for the future. It's going to have the answers, so the stretch Tisbol uses the accuracy right here and it knows the answers. But so you use the forecast because the forecast in the stretch Tisbol has the answers. But then the Tisbol eventually stretched too far out, which we see, which is making sense to me now. At the end of the stretch Tisbol, it then can't do the final thing right here. That might be our stretch Tisbol, yeah. At the end of it, it can't do these final 12 observations because the stretch Tisbol at the end of it is going to stretch beyond the data, which is fine, but it gets pretty much everything done. But the forecast right here, what it's forecasting, can't do it. So you have to not use a forecast to get the accuracy of your original models, but when you use the time series cross-validation, you use the forecast and check it against this right here. So the forecast is actually saying, here's the predicted values. We're checking it against these values. The model itself will look at itself and see how it's doing. We're not going to use a forecast for the original accuracy. Okay, so we've got our first one. We've got our second. Let's overwrite. And we're about to make this look pretty and interpret it here in 2 seconds. Okay, so we've got both. Now we got both. Okay, there's data frame 1. There's data frame 2. What I'm going to do to these two things right here. What will I do to these two things? I've got 2 data frames stored. Robind, 100 points right there, Robind. Let's call this table Robind of data frame 1, comma data frame 2. That's my table. Now, what I would probably do right here is I'm going to reorder the table. I'm going to go to table, store into table, rows 1, 1, 4, 2, 3. Whoops. Hopefully that didn't destroy it. Forgot my comma. And now let's take a look at the table. What did I do right here? If you look at it, we have a great job, Noah, right there. We're going to bind them. We have the naive training, the naive test, the drift training, the drift test. Now, Shreya, this is even worse than yours last night, and we'll explain why here in a second. Last but not least, let's go grab from the 475 Discord the cable way of doing it. And then, Jessica, we're going to do the man goes to a city. I need to go to 475, and I need to grab the code for the cable that we created. Where's 475? There's 475. Okay. Here it is right here. There's the cable. Okay. So this is code we dropped on how to make a really nice cable. This controls the way the rows look. So we've got, let's go row 1 and 3. That'll be good right there. The top one will be, that's good right there. I think everything looks good. We just need to drop this in right here. Oh no. What's it not like? Non-numeric alike in data frame, error in math, list. What was it? Oh, you know what it is? It's the round. Unexpected parentheses. There we go. Yeah. A little stretched. You know what we probably need to do? It's because of the... So it's these values over here. And that is row 3, column 3. 3 decimals. There we go. gosh. We're just changing decimals. There we go. How are we looking, Shreya? How does our table look? Thoughts on this right now with what we've done right here, the output we've created with model type. It's interesting how it kind of definitely changes. Oh, is that one? Does it not change? Oh, just look like that. Pretty good table, pretty good stuff. You can change the colors of the text. You can change the color of the header. Thank you so much right there. Sierra doing great help with this. We could also make a few last change right there to the row names of the table or the call names. Let's go to call names. Visually pretty nice. I like it. Call names of table. And let's throw into the call names. Let's go into here. Model, type, RMSE, MASC. Nope. And there we go right there. What's even better, if you're in 474, you could just go here, make cable. Now the problem is you probably want to specify a bunch of these arguments. But you could go and make cable function. And watch this. We could now go down here and go to make cable. And inside of make cable, we could just put our table and it makes the cable. So this is kind of the neat ways of doing is you could make your own custom function instead of having to remember all this right here, copy paste it. You could make a function called make cable, but you don't have all the options. We could start to change things, and sometimes it works better just to use the native function because now if our table looks differently, it's not going to make the same way. If I put inside of here df1, it might get really mad. Yeah, the limits are out of bounds, so it's going to get mad. What if we put in fit2? See, it looks a little bit different. It still makes it of sorts. Just doesn't do the row coloring, but that makes it into a cable right there. Puts the top one. We probably would want to do something like remove the 1 and the 3 or something, but yeah. Anyways, that's kind of the neatness of turning things into automatic functions right there that you can do by doing user-defined functions. So wait, let's analyze this real quick, and then we'll head back over to 201. Okay, Shreya, why is this so bad? Now, you can't compare these metrics right here. You can't say, okay, which I hope I made clear last night. You can't be like MASC is better because it's a totally different way of calculating something. It's just this is like the way he calculates his thing. This is the way we calculate it. But these are different things. This is like someone who likes to play PlayStation. This is like someone who likes to play Xbox. They're totally different ideas. Does that make sense, Shreya? Like you can't say like, oh, this is lower, so it's better. It's a totally different thing. And this is higher, so it's worse. No, it's a totally different thing. It's just like, do I want it to go this way or this way? If you were to go with the way I do it, you would only look at these values. Like statisticians will only look at those values there, or they'll only look at these values right here. So in truth, you don't need both of them. Rock knows. It doesn't matter. You just pick the one you like. Like you go by a standard. Like statisticians say, I use MASC to compare my models. That would be Rob Hyman right there. Would be looking at that, Dr. Hyman. And I'd say, I use RMSE to compare my models. So if you use RMSE to compare your models, the training says you have a typical miss when predicting the arrivals of 2.49. Pretty good. The drift is even better with a typical miss of 2.04, predicting the probably millions. And there you go. No resos right there. So these are pretty good, right? On the data, we do pretty well. On the original data, we do pretty great, right? But then when we go over to the test data, what happens? Our error is what? When you go over to the test data with the drift model, which is your best, your error is what? What does that number mean on the screen right there? Your error on the test data is what? It's 3.55 times worse. You got a typical miss of 2.04, and then you jump to a typical miss of 7.26. So guess what? What's that mean for our drift model? This is really sad right here. What's it mean for the drift model? If you see that your error is 350% bigger, your error is 355 times worse. What's that mean? This is literally where we're at in 474 also. That means what for not just you toss out the model. You say this is garbage. So the model falls apart when you actually try to use it. If you were to use this model to make predictions, like had you been using the model to make predictions, you wouldn't been getting a 2.04 error. You would be getting probably about closer to 7.26. The cross-validation, the test right here, is your best estimate of how your model actually does. and you want these two numbers to be as close as possible. The closer these numbers are, the better. So we'll try one last model in here. We'll just do it on the test data. Then we got to do one more thing. Here's our stretch Tisbol, and this shouldn't take too long, but this is where things can get crazy. If you do the auto ARIMA, it can take more than a moment, and this is a small data set. Warnings, NAs produced, dun dun dun. Might not be able to do it then, we'll see. Okay, there's our fit 2. I think it didn't get it. Oh, it did! The ARIMA does what? Well, that's not the ARIMA. Whoops. That's the naive. The ARIMA does meh. Why am I like, I look at the ARIMA and I'm like, meh. And Rob Hyman would say, meh, meh. I say, eh. It's not a big difference. And on the original data, we're getting errors like this. What we're seeing right here is we're not getting good ability to show. Yeah, it's about the same as the drift. It's a little meh. That's our statistical language, Michelle. That's how us statisticians talk about it. Meh, eh. This one's double meh. Meh, eh. This one's meh. This is a difference right here. Like, but it's still really bad. So you have to think about what this means and how much better we're doing. So you want to see a much smaller ARMA MSE, which is basically residual. If you're in Stat 201, these are basically residuals. Last question, 500 points. What letter on the screen stands for residual? 500 points, 475. Then we got to do a 201 question. What letter on the screen right there stands for residual in your predictions? So there's a letter right there that stands for residual in pretty much all but one, except for ACF. Oh, not the ACF. The ACF is the autocorrelation function, which does deal with the series explaining past series. The letter on the screen that is the E. Root mean square error, mean absolute error, mean percent error, mean absolute percent error, mean absolute scaled error, root mean sums of squared error. Maybe I don't use RMSSE. No worries. Good at 100 points. Noah, taking a shot at it. Let's do the 201 question. Here we go. Shreya, that was such a good review. Thank you so much, Shreya. Does that help with your understanding? The whole point is you just make a bunch of models. You see how they do. You find your best model. No, Noah, you're doing great. And Shreya, great understanding. I was talking to Dr. Petrie and telling him about so many of our great students. And I just want you to know, Shreya, that like I told him about a lot of students. I was mentioning like so many students, and I just want you to know, Shreya, that I was like, you know, because talked about what you were planning to do, and I was like, yeah, like, so I just want you to know. And no, I want you to know also you're doing great. Like, you both were in the chat right now just talking, so I want you to know that, you know, I really appreciate all your hard work asking these questions. That's the thing that, I don't know, what gets me really excited is like wanting to know why these things work. I think that's the questions I ask about the world. It's like, wait, why does this work? Oh, Michelle, you're great too, Michelle. Michelle, no. Michelle, 100 points, Michelle. Your mother's gonna cry. Oh, Michelle. Sorry, I don't mean to put anyone on the spot. Oh, I feel bad now. I literally, what I did with Dr. Petrie is I sat down and I listed every single student. I didn't leave one student out. He said, Brian, I said, all my students are amazing. Everybody. No, anytime. I talked to him, you know, we talked about all the stuff. We talked about the analytics program and stuff like that. And I talked to him yesterday morning, so it was like on my mind. And so, yeah. Let's do a man moves to 2 cities. We're going to speed run a little bit here. Speed run. Where'd the question go? Man moves to 2 cities. Speed run in question, Tom. I'm going to have 2 classes in spring with one of them, or maybe one with each, with Dr. Petrie, maybe? Shrey, I'm super excited. We need to get the Mario Kart thing going. I'm going to be focusing on that as, like, we got a little bit of a break coming up next week. The speed one with you as the Joker was my favorite. Nice. Yeah, that's my favorite too. Had my long hair. I did some tinting to the screen. That was really fun to do. People love that video. I was like, you know what? Let's just do it. Here we go. We got a man moves to 2 cities. Let's mark this. I like throwing in some randomness. You never know when it's going to happen. You're welcome, C. Shrey. I'll see you in a little bit. Man moves, chapter 17. Man moves to 2 cities. Or bike routes. Bike routes. Some jokes of that. Okay, we are speed running this question. If you want, I can send you a version. Email me. I'll send you a longer version of this question, but we are speed running it. And the number one thing, if you are short on time, is you need to know that
notation, brother.
Thank you, Leo. Leo was the one who helped us inspire to make that sound clip right there. So knowing the notation is the key to speed running all of these. When you get the test, you need to know the formulas. The formula to solve this question for a confidence interval is going to be y bar 1 minus y bar 2. That's the difference between the two sample means, plus or minus t with degrees of freedom that we had to find via an applet, which you won't find on the test. Star means you get to pick it, square root s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. This quantity is known as the standard error. So we have right here the difference between two sample means plus or minus a t statistic, which is going to be based on the confidence level and the degrees of freedom used for the t, times the standard error. This quantity right here is known as the standard error of the difference. So now that we know what we're working with, it comes down to finding the values in the formula, finding the values up top. So let's go mark them. Now what they do right here, you have to be very careful, is they do b minus a. So be very careful you do it correctly. It's easy to make a mistake. The average for B is this right here. The average for A is this right here. It is B minus A. They do it that way, so it's going to be 43 minus 42. T statistic we'll worry about here in a little bit. The standard deviations really doesn't matter which one you put where.
It doesn't matter!
Because he's going to drive each route in this scenario. There we go. They're going to drive the route 5 times each. And we've now identified almost all the notation. Now, this is where we're going to do something that's not on the test. What we're doing not on the test right here is we're getting the degrees of freedom via a degrees of freedom calculator. If you notice, the standard deviations are 2 and 4, and they drive each route 5 times. That's 2, 4, 5, 5, because 5 times driven for each route, and 2 standard deviation and 4 standard deviation. And here's the 2 sample t degrees of freedom calculator. We put in 5 for the sample sizes for each round and 2 and 4 for the standard deviations, and there's the degrees of freedom. It's basically 6. This is going to be an interesting question today. We have to take this value now over to a t-applet, and we will give you the t statistics on the exam, because we don't expect you to find a t statistic by hand, to find a confidence interval, I should say. So this is where we put in the degrees of freedom right there, and we enter in what percent confidence are we. We are 95% confident, which is actually on the screen, but I prefer to show my 95% confidence intervals by graphing the middle portion to show this is the middle 95%. Now I'm a little bit worried, and that's why I was worried. So we're going to try calculating this both ways. But because of the low degrees of freedom, usually we don't think about it like a decimal degrees of freedom. We're going to see what happens. There are more exact applets for this, and I'm going to go find one really quick. I'm going to see what happens if I were to have used that value too. So t-applet Iowa. This is Matt Bogner's applet, where he does super exact calculations on it. And we want 0.95 in between. He's saying the t, that's the, oh, I did 0.9. I thought that was wrong. Okay. 2.4. And is he doing that same? Okay. He says it's 2, because he can do his exactly. That's interesting. He says it's 2.45 or 2.46. I'll drop this in the chat. If you get this one wrong by a decimal or two, tell me. You're supposed to use the t, though. A lot of people use the z by accident. This one's a little more complicated, why I'm not a big fan of it. But with the degrees of freedom so small, every little bit makes a difference. And I'm wondering if that would cause a problem, and I fear it would because it's going to make the interval a bit bigger. We got just a few minutes to go right here. So now we need to solve the numbers in the equation. 43 minus 42 were the two sample means up top. Plus or minus, let's use the number I'm afraid of first. Let's do it the way Brian said to do it by going to here and see if we get the right answer. I think we should. We're going to take the t-statistic of 2.57. Square root, it was 2 squared over 5 plus 4 squared over 5. That's 16, that's 20. That's square root of 4, which is 2. Wow.
Wow.
Double check that. 4 plus 16 divided by 5. Of course it is. Yeah, I can do math. Okay, so that's 2 times 2.57. And that means the plus or minus right here is 5.14. And this right here is 1 because that's the difference of those two numbers. And there's the interval right there. If we subtract and add, we get, let's do the higher number is 6.14. And then the lower number is 1 minus. And that's negative. Do you only drive each route that many times? Okay. I'm a little worried. 95% confidence. He drives each route. Oh no, he drives each route 10 times. I was like, I haven't seen it. Okay, the t-statistic's completely wrong. Oh, this is what happens when we speed run something. This is what happens. Did anyone notice that? No, someone's watching this. And then they say, what did you do? I was like, I don't think I've seen this version where it's that small. 13.23, which changes the t-statistic. And the t-statistic is now 2.16. So the t-statistic is 2.16. I'm so sorry. Might be better if you watch the video on this where I do it a lot slower. Because that's going to change the t-statistic to 2.16. Degrees of freedom, I was like, something seems weird. My brain kept being like, burp, burp, burp. So 2 times 2.16, there's the margin of error, 4.32, 5.32, and then minus, not trusting my brain today. And then there's that. Okay. That'll be right now. I knew something was off. I could feel it. Okay, so the interval goes from negative 3.32 to 5.32. Should the man believe the claim that he can save 5 minutes? Yes, because there is a 5-minute difference. Yes, because the interval contains the 5-minute difference. Oh no, what did we do wrong? Did we subtract them incorrectly? 43 minutes on B, 42 minutes, standard deviation of 4, standard deviation of 2. Let's look at all. I know the error. This is why you mark your notation. I was just doing this as a test to see if you knew how to do your notation. Brian does wrong notation, gets problem wrong. That's what happens. So that's 2 times 2, that's 4, 16, that's 20 over 10, that's square root of 2, which is 1.414. So I think it is 1.414. 2 square root, there it is, 2.16, there it is right there, standard error of 3.05. So 3.05 is going to be 4.05, and so 1 minus that is negative 2.05. Now 5 is not in the interval. And there, we go right there. Boom! I was just seeing you. Michelle knows the notation. You get the notation wrong, you get the whole problem wrong. So this thing right here where I said that was N, no, that was not the sample size right there. Michelle, thank you for being here. This was a test to see if you know how to do notation better than Brian. Thank you, Jessica. I'm glad that made sense. I'm glad you're like, it makes sense. And I'm like, oh my gosh, I just totally... We were on a streak of like no problems wrong for a long time. And then Brian went and put the wrong sample size in, getting the wrong standard error, calculating the wrong t-statistic. You know what? Got to remember.
Notation, brother.
You get the notation wrong, the whole problem goes sideways. So he drives each route 10 times. The claim is 5 minutes. Oh, thank you, Sam, right there. Or just having some fun, making mistakes together. So there you go. If you do the mathematics correctly, a lot of times the hard part for people is calculating the t. But if you do the mathematics correctly, mark your standard deviations, mark your sample sizes correctly, mark your two means, find the t-statistics. You're welcome, Jessica. And if you're stuck on any problems, let me know. And Jessica, thank you so much for working ahead. I think this one's due on the weekend, which is going to be here before we know it. Harder problems. You know what's really cool? Watch this. If you wanted to do a two-sample t over here, t.test, and then you just go into here and do the following. Go data, bring up your data, and we'd actually need two data sets. Let's go here to MT cars. We would want to see maybe if there's a difference between which is ridiculous, the miles per gallons of a car and also the cylinders of a car. And there you go. There's a two-sample t-test like that. And there's evidence of a difference. P-value very low. Interval does not contain 0. And so that's how quickly we can do it with this. But we should also know what the formulas mean and what's being tested here with the T, the degrees of freedom, the hypothesized value, the P-value, and the interval to estimate the true difference right here. That's the two-sample means. Yeah, oh, and the Kahoot coming up. Until then, bye for now, everybody. Let's do it Sunday night. Sunday.